Today we're going to be talking about solving simple linear inequalities. And by simple, I mean that there's no two parts to the inequality, there's just one part, and it really more resembles a linear equation with an inequality symbol to capture an entire set of solutions. So when you solve a linear inequality, it might look something like this, where you have something like, let's say, 2x minus 1 is less than 7. So you would just sort of solve it pretending that less than symbol was an equal sign, and you would say, okay, all of our variables are already on one side. I got to get all my constants to one side, so let's undo subtracting 1 by adding 1. Then I'm left with 2x is less than 8. Then I want to undo multiplying by 2 by dividing both sides by 2, and I'm left with x is less than 4. And what that solution set means is any number less than 4, if I plugged it into 2x minus 1 is less than 7, it would be true. For example, if I plugged in x is 0, I'm left with the statement negative 1 is less than 7, which is true. Versus if I plugged in 10, that would leave me with 19, and 19 is not less than 7, so plugging in 10 would not work. Rather than trying to list out literally every single number in the universe that is less than 4, which would be an impossible task because you can't possibly capture that many, decimals, fractions, etc., all the way down to negative infinity, what we do is we express the solution with an inequality. Now, to express that solution with an inequality, we got to get this notation straight. So if we have all inequalities are read left to right, and if I say x is less than 4, that means x is a number strictly smaller than 4. 4 itself does not work. If I stick a line underneath, now it says x is less than or equal to 4. Now 4 itself is considered a kosher solution. I could also flip this around, and it would express the same set of solutions, but the language would be flipped around. Because now I would be say 4 is greater than or equal to x, which is an equivalently logical statement to x is less than or equal to 4. Now, that can get confusing, so I strongly recommend keeping your variables on the left-hand side whenever possible, because since inequalities are read from left to right, if you keep that variable on the left-hand side, you will be a little bit more consistent in your thinking about the solutions. Just as a quick check for your understanding, go ahead and pause your video and try out this example. What would be a value of x that would make this statement true? So for this example, it's probably going to help to visualize this on a number line, because if I have 0, I've got negative 4 here and positive 4 here. And if you think about positive 4, numbers smaller than positive 4 are to the left of 4 on the number line. And that's true with negative 4 as well. So it would be any number to the left of negative 4 on the number line, which would be numbers such as negative 5, negative 5.5, negative 6, etc. So any number that you listed that would be more negative than negative 4, like let's say negative 7 and 1/2, why not? That would be a number that would work in that statement. Now this graphing I just did, there's actual logic on how you do that. To graph inequalities on the number line, this is actually standardized. You use an open circle if it is not allowed to equal that number. So if you're using either just the strictly less than or strictly greater than symbol, and you use a closed circle if you are allowed to equal that number, so the or equal to symbol. You then will draw an arrow either pointing to the left to indicate more negative, so this is the less than direction, or to the right to indicate more positive, which is the greater than direction. And then we do also have compound inequalities. This is something that we're going to go over a lot more in our next video, but you want to think about and statements mean that both of the inequalities are true at the same time, while or statements just means one of the inequalities is true. But we'll go over that again a lot more next video, but we'll touch on that a little bit here. So for example, if you have the statement x is greater than or equal to 3, what you want to do is either locate or sketch out 3 on a number line. You're going to want to use a closed circle because it's allowed to equal, and then you'll want to shade everybody to the right of them, as was sort of already pre-filled out for you. Go ahead and see if you can do these next two on a number line yourself, though. So this next one is read off as x is less than 5. So I'm going to use an open circle to indicate we cannot equal 5 itself, but we're getting really darn close. Numbers such as 4.999999 are okay. And then we're going to shade to the left, and that would be the solution set x is less than 5. For x is greater than or equal to -2, we're going to use a closed circle on -2 because it's allowed to equal -2, and then shade everything to the right. And you can do just a quick sketch even if you're not given a number line. Let's say you were given this statement. Actually, we'll have it there. And then let's say it was a -7. If you want to sketch this, what you would just do is make a reference of 0, make a reference of -7, use a closed circle for -7 to indicate or equal to, and then shade everybody to the left. In most instances, you don't need to make little tick marks for every single integer in between 0 and -7, particularly now that we're very used to dealing with fractions, decimals, that sort of thing. You're never going to literally list all the numbers on the number line. They're in between 0 and -7. Not physically possible. Totally fine just to have a reference point in the number in question. Of course, number lines and inequality symbols are not actually the only way to express solution sets. A way that you're going to see happen all the time throughout your collegiate career is actually interval notation. And what is interval notation? Well, it basically is shortening the language on the number line. So what does that mean? Let's say you had this previous example, -7 and everybody less than it. The way this interval notation would express this is it would say, okay, this lower bound that you're approaching is really -infinity. This number line is expressing that we go all the numbers to the left as negative as possible, -infinity. Comma, your upper bound is -7. So it's always your smallest term, comma, your largest, and if there is no smallest term, it would be a -infinity. If there is no largest term, it would be a positive infinity. You then use a parenthesis on infinity always, just because we philosophically can't reach it. And then you would use a bracket on the -7 to indicate or equal to -7. And that's what this is saying in kind of some more words. So you always work in the same order as the number line. So you always do the smaller number, comma, the bigger number, also known as the lower bound, comma, the upper bound. The first number is always your lower bound of the inequality, it's always the smallest one. If it just keeps going forever in the left direction, that's a -infinity. The second number is the upper bound of the inequality, your largest number. If there is no upper bound, that means you go forever in the right direction, that's a positive infinity. So a parenthesis is always used for the less than or greater than symbol whenever you are saying we are not actually including this number. We can get really darn close, but we're not including it itself. Philosophically, infinity is always a parenthesis. That's just no matter what. Versus a bracket is if it is equal to. And technically there's also just a straight up equal to versus not equal to symbol as well that would sort of be included in it. And that's sort of the summary on this chart. Now, these compound inequalities we haven't gotten too far into yet. But whenever you have them, if let's say for example x is trapped in between a and b inclusive, then your lower bound is literally a, your upper bound is b, and then you use brackets on both. You can indicate, oh, we've included one bound but not the other by using a combination of brackets and parentheses. For simple linear inequalities, you're probably going to be mostly using the second half of this set whenever you just have a bound and then either going up to positive infinity or down to negative infinity. By set builder notation, we really mean this first column. For the set builder notation, you'll notice that that's basically the same as the inequality. What we've just tossed in, though, is that we've specified our variable, and we've used this straight up and down line that means such that. Mathematicians are very lazy. We like to shorten notation when we can, and we've decided that we write the words such that so often that we might as well include it just as a straight up and down line. So go ahead and pause your video and see if you can write down all the notations for a number less than or equal to 9, a number indicating that that should be your variable. So for this, if you were to write in set builder, you would use the little squiggly braces. You would specify your variable such that, and it says that number is less than or equal to 9. So that would be your set builder notation. I actually think that the interval notation is easier to draw after the number line. So I'm going to have a reference of 0. I'm going to draw a 9. Since it's or equal to, I'll use a closed circle on the 9. And then it says less than, so we're going to shade to the left. Now that we see this, we see that this implied lower bound is negative infinity, comma 9 is the upper bound. We're going to use a bracket on the 9 because he's included, and philosophically we never include the negative infinity, so it is a parenthesis. And this is really just the language part of math. If you weren't ever taught this, there was no reason you would come up with this language in the system. But once you learn the language, that's the translation that you're doing. This was touched on very briefly before, but to be very explicit, the way that you solve an inequality is going to look extremely similar to the way you solve an equation. So you still want to start with just simplifying both sides of the inequality, distribute, combine like terms, that sort of thing. Then you want to move all variables to one side, all constants to the other. It's not necessary, but it's recommended you try to keep your variables to the left, just because you read these off left to right. So if you keep them on the left, you're not going to get potentially confused about the direction that you'll be shading. You want to be sure that you just solve using the typical inverse operations, except there's one very key difference that you have to keep in mind, that whenever you multiply or divide both sides of the inequality by a negative number, you have to flip the inequality sign, as seen in this example. So you would start off normal. You would say, okay, I want to get x by itself. Let's undo adding 5 by subtracting 5. Great, we're left with negative 2x is greater than 6. But then when you go to divide by negative 2, the inequality symbol flips. Now, why is that? Well, let's think about a very simple example. So if I have x is greater than 1, if we were to graph that on a number line, we would put an open circle on 1, shade everything to the right here, and then I wanted to know how negative x is related to 1. Well, negative x says flip the sign on the number. So all these numbers here to the right of 1, once I flip their sign, they're going to be less than that 1. And in particular, they would be also less than negative 1. If I were to then solve that, I would end up dividing both sides by negative 1 by negative 1. And it's not the case that x is less than positive 1, but x is greater than positive 1 there. So that's just a little bit of intuition on why it works. I would recommend sort of with that example I just did, maybe try to plug in a few numbers and sort of see how that plays with each other. But regardless, the short of it is that you do need to remember to flip the inequality symbol anytime you multiply or divide both sides by a negative number. That's really the key thing. So with that in mind, I'm going to encourage you to go ahead and try to pause your video and solve these inequalities and then come back to see how your solution compares to mine. So for this next one, first things first, I want to get the x's by itself, preferably on the left-hand side. So I'm going to undo these constants. So I'm going to subtract 2 from both sides to undo adding 2 on the same side as the x. So I'm left with negative 2x is greater than or equal to negative 4. Then I'm going to divide both sides by negative 2 in order to get rid of multiplying x by negative 2, and then that will cause this inequality symbol to flip around. Keep in mind that the inequality symbol flipped around because I was dividing by a negative 2. It was coincidence that the right-hand side also happened to be a negative 4. That's not what caused it to flip. Then if I want to express my solution in interval notation and graph the solution set, I recommend graphing first. So we're going to have a reference point of 0, put 2 to the right to it, You're going to use a closed circle because it's or equal to, and then you're going to shade to the left because it is a less than symbol. So that means that the lower bound here is a negative infinity, and we always use a parenthesis on infinity because infinity in positive or negative can never be reached philosophically. And then our upper bound is 2 because that is the largest number our x is allowed to equal. And then we'll use a bracket on him because we are including that number, not excluding that number. Sort of similarly on the next one, again, I want to move all variables to one side, all constants to the other, and it's recommended you keep your variables to the left just because you'd read inequalities left to right. So I'm going to move the 3x over by subtracting 3x from both sides. The 3x minus 3x cancels to make 0, and I'm left with negative 7x plus 35 is less than or equal to 7. Again, my goal is to get x by itself, so I'm going to subtract 35 from both sides. I'm left with negative 7x is less than or equal to negative 28. And as a last step, again, my goal is to get x by itself, so I divide both sides by negative 7. Negative 7 divided by negative 7 is 1. And I am left with x is now greater than or equal to positive 4 because I had divided by a negative. If I'm going to graph that, I'm going to put a reference point at 0. I'm going to plot the 4. I'm going to use a closed circle on the 4 because it's or equal to. Then I will shade to the right because it's greater than. And then our lower bound is 4 because it's the smallest number we're allowed to equal. Our upper bound is infinity because it keeps on going forever to the right. We're going to use a bracket on the 4 because it can equal 4, and then a parenthesis on the infinity because we philosophically can never reach infinity. This next one involves a little bit more simplification, so we're going to make sure that we simplify both sides of the inequality first. In particular, we're able to distribute, so we end up with 5x minus 50, and then we're going to drop down to minus 2 is less than negative x plus 7. If you notice, I rewrote negative 1x as negative x. It's tomato, tomato. Then we're going to continue to simplify our left-hand side a little bit more, so we'll have 5x minus 52, because negative 50 and 2 are like terms, is less than negative x plus 7. And then our goal again is to get x by itself, and it's recommended you keep your x's on the left-hand side if you can. So I'm going to add x to both sides, add x. That will cancel out to make 0. I'm left with 6x minus 52 is less than positive 7. Again, my goal is to get x by itself. So I'm going to undo subtracting 52 by adding 52 on both sides. I'll be left with 6x is less than 59. And then as a final step, I'm going to divide both sides by 6. And I'm left with x is less than 59 sixths. Now 59 sixths is not a fraction that simplifies. 3 doesn't go into 59, 2 doesn't go into 59, therefore this can't be simplified. And then if I were to plot it, I know that 59 sixths is bigger than 0, so I'm going to draw it to the right of 0. Then I'm going to use an open circle on 59 sixths because I'm not allowed to equal 59 sixths, and then shade to the left because it is allowed to equal any number smaller than 59 sixths. Last but not least, let's talk a little bit about how we might apply linear inequalities to a real-world scenario. So here we have a company that's making a profit, which means that it needs to make more money than it pays out, paying out costs of running the business, your salaries, your rent, etc. So suppose its revenue, which is strictly just the money that's being brought in, is represented by R is equal to 150x. And it costs 80x plus 30,600 in order to run the company. How many items need to be sold to make a profit? Well, if it's going to make a profit, your revenue will have to be strictly larger than your costs. If it's equal to, you've only broken even. And if it's less than, you're losing money. Then you're going to want to actually plug in your values. So revenue is 150x. Costs are 80x plus 30,600. And then our goal is to get x by itself so that we can isolate how many items we need to sell. We want to move all x's to the left, keep all constants to the right. So I'm going to subtract 80x from both sides. 80x minus 80x makes 0. 150x minus 80x is going to leave me with 70x is greater than 30,600. Then we're going to divide both sides by 70. In order to do that division, you can either do it the long way or the short way. I'm going to go ahead and just do this the long way to the side. As a pro tip, if you notice that both of these end up ending with a 0, you can actually effectively just move the decimal point on both at the same time. The decimal's normally here, move it here, decimal's normally here, move it here, sort of pre-divide both numbers by 10, if you will, and then you'll be left with a simpler problem of 3,060 divided by 7. 7 goes into 30 4 times without going over. 4 times 7 is 28. 30 minus 28 is 2. Drop down the 6, drop down the 0. 7 goes into 26 3 times without going over. 3 times 7 is 21. 6 minus 1 is 5. Drop down the 0. 7 goes into 50. We're blanking, but 7 times 6 is 42. And then another, oh, of course, 7 times, because 7 times 7 is 49. So we get 437 with a remainder of 1. So if we're thinking about a real world scenario, if x was exactly equal to 437, then you wouldn't be making a profit. So x has to be strictly bigger than 437 to make a profit, because these items are only produced in whole numbers, which means that x has to at least equal 438 items. So if you were to express it as an inequality, you would say x has to be bigger than 437, potentially with the exact amount, 437 and 1/7, or you could do a decimal approximation. Most likely in a real world scenario, you would do the rounding and say it needs to be a whole number bigger than 437, or at least 438.